Right? This is a Hall effect lah. This is your conductor or semiconductor. There's a magnetic field perpendicular to one phase. There's a current flowing through another phase. Current flowing one direction, magnetic field in one direction. Then you have observed that there's a potential difference across the two phases. And that potential difference is called this is known the Hall effect, and the potential difference is called the Hall voltage. Right? That's why we connect a voltmeter here, we can measure the voltage. Right? There's your current, one direction, the length, right? Magnetic flux density on one surface, right? 1, 2, 3. Right? The third surface is your Hall voltage. And this is usually thin. This is called the thickness. Okay, today we will derive the equation for you. This is what you are expected to remember, this equation. Right? We won't ask you to derive, but you need to use this equation to derive Hall voltage. Okay. Right? There's your width, there's your length, there's your thickness, there's your conductor. It can be conductor, it can be semiconductor. There's your B. Right? B is parallel to the thickness. Remember that? Yeah, you're required to identify the thickness. B is in the same direction as the thickness. Right? This is the surface for measuring B. And there's your current flowing in. And there's your Hall voltage. Right? Where you have your thickness. There's your Hall voltage. Okay. If you like, it's on the surface parallel to current. You need to identify the Hall voltage. Hall voltage is given by the formula. Right? The K is a constant of the conductor given by 1 over N QT. T is the thickness. B is the magnetic flux density. I is the current. Hall effect can be used to measure electric field with Hall probe. Hall effect can be used to measure magnetic field. You will see that. That's why this one is thin. Thickness. There's a field. There's a current. Be prepared to see the different orientation of the current, the field, and then the Hall voltage is on the side parallel to the current. That's the equation you need to derive, given in the formula sheet. NQT is a constant of conductor or semiconductor, is in Coulomb per meter square. If a slice is thin, then the Hall voltage is large. If we set I constant, sorry, the dot is a bit messy. VH is proportional to current. Right? Or voltage is proportional to current. Proportional to B. So VH can be used if you keep all the this is constant. Right? If we keep I constant, then VH is proportional to B. So by measuring VH, we can calibrate to measure B. To calibrate, when we calibrate the voltmeter, and instead of having a voltmeter to read voltage, we calibrate to read B lah, magnetic flux density. Means we can change the voltmeter reading to give directly B. Right? To calibrate, we put a probe in a known field. Right? B is known. And we note your the V1. We know your V1, the known field, and we know the current, put an ammeter across there. Then we can find K. Right? V known, B known, I known, K can be found. Okay, so K can be found, and we have this formula. Either we convert or we make a scale for B on the voltmeter. Hall effect is the production of phenomenon, is a conduction phenomenon, which is different for different charge carrier. In most common electrical application, the conventional current is used partly because it has no difference whether you consider positive or negative charge be moving. Okay. We can study the charge carrier in a conductor or semiconductor. What's the charge carrier that's moving? So in this case, there's the current is a conductor. So which side is going to be negative? Using your Fleming's left-hand rule. Yep.
Okay.
Field going into current move from left to right. Where's the direction of the force? Can direction of the force.
Force is the thumb.
Where's the direction of the force? Now, force is the thumb.
Is it up?
Yep. So which side is negative?
Left?
No. The force is acting on the charge carrier. So the top must be negative.
Oh.
Top must be
Oh, okay,
negative.
okay.
It's deflected by the magnetic field. Right? So it depends on whether the charge carrier is electron or positive charge. So this side will be negative if the charge carrier is electron. Right? If we use semiconductor, okay, hole you can think as positive charge. Which side is going to be positive or negative? Same. Semiconductor, there's your current. Which side is going to be positive
Positive?
or negative? Which side is positive? Which side is negative?
Top.
Right, same. The force is still outwards, but hole is positive charge. Right? So this side will be positive. The top side will be positive now because it's acting on the positive charge of hole. Right? Bottom is negatively charged. Right? So we can use the Hall effect to study what is the charge carrier in a conductor or semiconductor. Okay,
Okay.
okay. A conductor placed perpendicular to the magnetic field. There's a conductor. There's a magnetic field perpendicular to one of the face. There's a current moving into the conductor. Oops, give you the answer already. Where the direction of the force on the moving charge? Yep, direction of the force on the moving charge. Use Fleming's left-hand rule.
Looks like up lah.
the field is going in, the current is going from left to right. So the force is upwards. So, okay, but it's acting on electron. Which part of the conductor has a higher potential? Yep, which part of the conductor has a higher potential? Remember, the force act on electron.
Which part?
Which part of the conductor has a higher potential? Force is
Up.
upwards, huh?
Yeah, up.
Upwards, so it's acting on electron. So the electron will be deflected on this side. So this side will be higher potential, this side will be positive. Okay,
Oh.
which part is the thickness?
What does it mean by is the thickness? Teacher, what is the thickness?
Length of the conductor is where the current flow. That's the width where the
Oh,
field is going through. And then there's the thickness of the conductor.
okay.
Right? You need to know how to identify all this. Right? So there's your thickness. So there's your thickness. Right? Thickness is always parallel to B. Okay, so as the current flows through, the electron will be deflected outwards. So leave the positive charge at the bottom. So this negative charge and this positive charge act as parallel conducting plate. So it becomes a velocity selector. Right? As the charge move in the magnetic field, they experience an outward force. Right? Electron deflected outwards. The charge carrier in the conductor are electrons. These electrons are deflected outwards, leaving the bottom of the conductor positive charge. Electron flow in, right? Electron flow in from right to left, experience the outward force. The outward force deflect the electron outwards, so the bottom will be positive. So when it's stabilized, the current is constant, and the top will be negative, bottom will be positive, and current will just go straight through. When the flow of current stabilizes, the whole voltage appear across the conductor. That's the whole voltage. So with whole voltage there, right? Right? Whole voltage across the conductor produces the electric field in the conductor upwards. Right? Electric field is from positive to negative charge. The upwards magnetic field force is balanced by the downwards electric force on the electron. So there is your electric field. Right? If you look at electron, what are the forces acting? Magnetic force, BQV, there's a magnetic force outwards. When we have a whole voltage is produced, then you have a electric field there from bottom to top. So that electric force is E times Q. Right? They are both in different direction. So they are equal for non-deflection. When the current flows straight through, right? When the whole voltage is constant, the magnetic force equals to electric force. So we get our same formula as velocity selector, right? BV equals to E. Stop me if I'm going too fast. Okay, we are going to derive this equation. Right? We have just derived this equation. Same as velocity selector. I'm going to use this equation. Right? Remember to identify that is your A. This side is your A. Where the current enter is your A. Cross-sectional area. So it's T times D. Right? T times D. A replaced by E times D. Then from this equation, can get our V. V equals to NQA. A is your dt. E is VH over, right? VH over D. So replacing the V there, we got this equation B I N Q dt equals to VH over D. D and D cancel off. We got the equation. Okay, you need to know to derive and use. Any comment? If it's electron, we just replace our Q with E. Any
Okay.
question?
No.
No, okay. If the charge carrier is electron, then we have Bi over NET, net. That's how it looks like. Right? Sunway College should have hole probe. Hole probe is there. Just a tiny semiconductor there. Right? This is a probe. The whole thing is called a probe. The semiconductor is there. Right? This is the associated apparatus to measure magnetic flux density directly. Right? This gadget or apparatus or probe apparatus is to measure the magnetic flux density directly. Right? There's your semiconductor at the end there. Right? There's another type thing. Right? Semiconductor. Right? For measuring magnetic flux density. Right? Precaution. This is for paper 5. Probe must be placed perpendicular to the field. So how do we know that the magnetic field is there? How do we know it's perpendicular since we cannot see? Then how do we know that magnetic field is perpendicular to the semiconductor? We cannot see.
Mm. Using the FN rule?
Adjust, adjust until you get maximum value.
Oh.
You know roughly where the field is between the magnet. So you adjust until you get maximum value. So that is perpendicular. This one memorize in case it comes out in the paper 5. Surface must be perpendicular to the magnetic field lines. Adjust until the field is maximum. Measure using opposite phase and determine the average field. Right, one side and the other side. Right? That's how you put it. You can make your own. Okay, there's a hole probe. There's a current carrying wire. That's the equation. Does the hole probe depends on the angle between the field and the surface of the probe? Yep.
Yes.
Yeah. Right. We will study the next topic. The field is coming out circular. So it's perpendicular to the surface. So this is maximum. Yes, when the surface of the probe is perpendicular to the field, the whole voltage is maximum. As the angle changes, the whole voltage decreases. Right? As you turn this one, the whole voltage decreases. What happens when you rotate the whole probe about its axis through one revolution? That is the axis. Oh. That is the axis. What will happen? What will you observe? Right? First it will be maximum now. First it will be maximum, changes to zero, and then changes to negative maximum now, when the opposite phase is perpendicular to the field. Now. Okay.
Sine wave.
Sine wave.
No, no, no. Cos.
Sine wave. Sine wave. It is sine wave. If your rotation speed is constant, no? But you don't need to go that far. Lah. Right? These are various experiments you can think of. This is to measure the field using Hall probe, right? Within the solenoid. There's a power supply. There's the Hall probe apparatus. There's a solenoid. Or right? These are all set up. There's a Hall probe. We can increase this one by 1 cm, 1 cm on left side and right side. Then study how the field varies. Right? To investigate the variation of magnetic field strength along the axis of the two circular loop. Right? This is more for paper 5. Right? And this one we can do in the lab. Right? I take this photograph in the lab. There's your bar magnet. There's a hole probe. The cm ruler. Right? First you put it close together. Then you remove 1 cm to the right, 1 cm to the left. Then 1 cm to the right, 1 cm to the left again. No? And study how the field varies with distance between the magnet. No? Or flat coil. Right? There's your power supply. Right? We have the apparatus in the physics lab. This is your physics lab. Right? There's your ammeter room. And you can study how the magnetic field varies with distance from the center using the Hall probe. Any comment?
No.
Okay, let's do some question. Hope you have a chance to look through. Right? Page 178. Magnetic field is a last topic. So you can expect a question to come out. These are the various formula that you need to remember. This is a velocity selector, and a charge comes out from the source, perpendicular to the field, perpendicular to the magnetic field and the electric field. Okay, see whether you can remember what I taught you last week. What is the force on a charge Q moving with a velocity v at an angle to the magnetic field of strength B? Yep. What's the formula?
Oh,
Can you remember? Right?
Is it
This
like the
formula you can
uh
remember. Force equals to B Q V sine theta. What's the velocity selector?
what does it mean by
Yeah, what's the
oh
velocity selector?
mm, like only allows like a specific velocity to pass through?
It selects a velocity for particular charged particle using electric and magnetic field that are perpendicular to each other, which give deflection in opposite direction. Explain how a uniform magnetic field and uniform electric field may be used as a velocity selector for charged particle. Right? Same as number 2. Electric field and magnetic field at right angles to one another and give deflection in opposite direction. What is meant by specific charge? Yep,
How much electric charge
no,
and all
Q
that?
over M. Okay, now it's the ratio of charge to mass of the particle. Can?
QOM, right?
Yeah, Q over M.
Yeah.
Okay, let's try the velocity selector. That's your proton moving vertically downwards between two parallel plates. These are your two parallel conducting plates. Show the magnetic force on the proton. The field is coming out. Where the direction of the force on the proton?
Down.
Huh?
Is it down?
You're supposed to tell me using Fleming's left hand rule.
Okay.
Right? The field is coming out. The current is perpendicular, coming down. So where's the force? Right? You got coming out, you got coming down. So the force is either left or right only. Huh? Okay now. Got only 10 more minutes. Can
I got
current
left.
is current is downwards. So to the left, okay. There's a magnetic force. Show the direction of the electric field for no deflection. Where the direction of the electric field for no deflection?
Electric field.
Yeah, direction of electric field. You want for no deflection, the electric force is going to the right one.
Uh-huh.
So it means that the electric field must be to the right. Right? Yeah, this part is
Hmm.
higher potential display. Can?
Yes.
Right? So answer for you is part C, which plate is a higher potential display. Left hand plate. What happens if I replace a proton with an electron of the same speed? Yep,
Replace proton with electron.
replace a proton with an electron of the same
The
speed.
direction will change.
Reaction stays the same, right? Because our BV equals to E, velocity selector, that equation, right? Doesn't depend on the charge. For the same velocity, the electron remains undeflected, same as the proton, except of course that two force will reverse. electric force and magnetic force will reverse. Electric force will go to the left, magnetic force will go to the right. What happens if we replace a proton with a alpha particle of the same speed? Remember, alpha particle got two positive charge. Yep.
Higher force.
Yeah, what happened? Does it go straight through or does it go, is it deflected?
I think deflector lah.
No, it doesn't depend on charge. As we said, alpha has two positive charge, right? Two positive charge, the magnetic force is double, the electric force is also double, still balance the magnetic force, so alpha will just shoot straight through. There's the path is not affected. Okay or not?
Oh,
Okay?
yes.
Okay, testing you on electron volt. Choose the correct answer, and for the incorrect one, state the correct answer. 1 electron volt is a unit of energy. Is it true or false?
No.
True.
Oh, wait. Yeah.
Energy is defined as the energy an electron acquire when accelerated through a potential difference of 1 volt. Right or wrong? True or false? That's the definition of electron volt. True. If the electron is accelerated through a potential difference of 3 kilovolt, then it acquire energy of 3 kilo electron volt. Right or wrong?
Wrong.
Correct.
Wait,
Yeah,
what?
true. EV, right? EV. If you want to find joule, then you use EV to calculate. E is the charge on the electron. V is in kilovolt. So you get joule. So you divide by E, right? Because 1 electron volt equals to 1.6 and 10 to the power. Same as the charge on the electron. So you divide, you get 3 kilo electron volt. How about this one? Is it correct or not?
I think it's false.
False. What's the true? What's the correct answer?
True.
What's the correct answer?
Oh, what's the correct answer?
Ah, right. That's 1 electron volt. Is 1.6 and 10 to the power minus 19 joule. That one you need to remember. Same as the value for electron. So 6,
6.4 times 10 to the power
9.6 and
19.
10 to the power minus 19 joule is 6 electron volt. How about number 5? Is it true or false?
True.
True. Okay. See whether you can get the answer. An electron emitted with zero velocity from the cathode is accelerated through a potential difference of 5 kilo electron volt. What's the kinetic energy? Right? We use QV. So it's 5 kilo electron volt. Right? We want to find joule. Then electron is 1.6 and 10 to the power 19 volt. Right? Change it to SI unit. Velocity of electron are leaving the anode. Okay. Look to the formula sheet. Half mass of electron velocity. Okay or not?
Yes.
Okay. See whether you can remember your electric field strength or not. Upper plate 300 volt, bottom plate minus 300 volt. Separation is 2 cm. Calculate the electric field strength A within the plate and the force on the electron. See whether you can get the answer. Yeah, 300 minus 300 is 600. Oh. Separation change to meter. Right? Force is EE. Oh. Is the electron. Put in your value. There's electric field strength. There's a charge on electron. Can
Yeah. Yeah.
what happened to a stationary charge in the electric field?
Uh, experience. Wait.
A stationary charge Q placed in the electric field experiences electric force. A positive charge will accelerate in the direction of electric field. Right? All this must be on the fingertips. If the charge is Q and the field is E, what is the magnitude of the force?
F.
EQ, F equals
F.
EQ. What is the direction of the force on the positive charge? Right? There's a field. There's your field. There's a positive charge. Where's the direction of the force? Well, try the rest. Direction of electric field. That is the direction of the force of motion. Right? Try the rest while you wait. We will start a new topic. If got time, we will answer your question. Anytime he will disappear. Anything you want to ask or clarify?
Try the ones in there.
Try number 13 no? And the rest. Anything
Okay.
else you want to clarify?
No.